I'm Alicia Frame. I'm the Senior Director of Graph Data Science at Neo4j. And I'm here to talk about what's going on with graph data science. And I think because this is like a much smaller group, a smaller venue, we can be much more informal. I was very tempted to just be like, screw slides, let's just do an AMA. But we always like to have some conversation guidance. So I'm gonna be talking today about what is graph data science, how does it work, how do you use it? But I'd also like, if you have questions along the way, we're a small group, we can be informal, raise your hand, throw something at me, and let's just get, let's have a fun time. So we have just passed the 2-year mark for graph data science. We rolled GDS 1.0 out at the start of the pandemic. And when we started, we were like, we've got 5 categories of algorithms. We have an in-memory graph. Some of them are parallelized. We had a good solid foundation, but 2 years later, we've come a long way. We have 18 more algorithms than we had when we launched. We have graph embeddings, totally new from when we launched. Really powerful way of doing feature engineering. We have in-graph supervised machine learning so that you can do in-graph pipelines to predict how your graph is going to change. And it is so much faster. So Philip was really excited during the keynote to share those benchmarks. Those benchmarks are actually my team's internal guide star of where do we need to invest, improve to make sure we're the best performing out there. We also have really invested heavily in making sure that we can support enterprise workloads, making sure that we can scale into the tens of billions, hundreds of billions of nodes and function. So we've added things like MLOps support, improved compression. If you like compression, we're going to talk a lot about it. One of my engineers is going to talk a lot about it. But we've come a long way. And this talk is really framed around starting off with the basics of what the heck is graph data science, framing how we talk about and understand graph data science, and then talking about what the capabilities are. So 4th slide in the deck, here's the overview of the presentation. We're going to start with the basics. Some of you have probably seen these before, but I have learned my lesson. Whenever I talk about graph data science, I need to explain what it is, what I'm talking about. We're going to talk about the capabilities built into the library. So when we talk about graph data science, what does Neo4j do for you? We're going to talk about deployment, how and where you can run Neo4j graph data science. We're going to talk about the ecosystem. Some of you may have come from Zach's talk right before this, where he did a whole deep dive into the ecosystem. And then we're going to finish with new stuff, the latest and greatest, the most exciting stuff out there. And again, questions along the way, feel free to interrupt. So this is my TLDR slide. I use this one a lot. What is graph data science and why bother doing it? And the bottom line is your data is meaningless without relationships. So if you think about whatever domain you work in, right? If you just have the nodes, if you just have your rows, right? You might have items, customers, warehouses, stores, parts, suppliers. On their own, those don't mean a whole lot, right? You need the connections between them to answer any kind of question, right? Who bought this item? That's a relationship. Who manufactured this item? It's a relationship. Who works for who? Those are relationships. And so that context answers critical questions. Without it, you can't make sense of your data. And that's the bottom line for like why graph data science. You can zone out for the rest of this. This is the one important slide. But question 2 is, okay, cool, you just told me relationships are important. How do I use them? And what is this? And really, graph data science is just using those relationships to answer your questions. And typically, these are the kind of questions that you can't answer without a graph. If I want to know what's the shortest path between this warehouse and my customer, I need a graph for that. If I want to know how many communities do I have of purchasers in my retail network, you need a graph for that. So when we talk about answering questions with graphs, what we're really talking about is kind of 3 techniques. The first one, and probably the one that people are most familiar with in this room, is queries, right? That's graph data science. You're answering a question. You're finding the patterns that you know to look for. So if you work in fraud, maybe you say, hey, I'm a SME, I know a lot about fraud. People who interact frequently within 2 hops of a fraudster are probably committing fraud. That's a query that's answering a question. You can use that for feature engineering analytics. But as we get more sophisticated, we talk about actual machine learning, the cool stuff, what I focus on. This is your graph algorithms where you're finding patterns, you're using embeddings for feature engineering, you're making supervised predictions about how your graph evolves. These are answering questions too. And the third part is charts, right? You have to visualize your results. If you can't explain what you did, it doesn't matter how cool it is, you have to have a way of showing in plain visualizations, this is what I found and this is why it makes sense. And you need special visualizations for graphs. But taken all together, these are how you use connected data to explore and understand your domain. So how do we do graph data science? I like to think of it as a process. Step one is have a graph. Foundational, before you can do anything, is you need connected data in a connected shape. And if we go back to that Venn diagram, once you have that knowledge graph, once you have that connected data, then you can start finding the patterns you know to look for. Once you've got that though, the bigger your graph grows, the harder it is to know exactly what to look for, right? When you've got a small graph and you understand everything in it, sure, I can just write a query, it's easy. But as my graph grows, now I have tens of billions of relationships. What's important, where do I look? And this is where machine learning comes in. So this is where we're gonna start using graph algorithms, which are unsupervised techniques. They learn from your data, from the connections you have, to answer certain types of questions. So what's unusual? Where are there clusters in my data? What are trends? What looks similar? So it helps you sift through those billions of data points into the most relevant ones, the most unusual ones, what's gonna happen next and where you need to focus. And then as teams get even more sophisticated, you move from the unsupervised world of graph algorithms into the supervised machine learning space. And this is where you're using your graph as your whole input data, right? You're learning from the structure of your graph to predict how your graph is going to change in the future. So you're probably using an embedding for feature engineering or some of those algorithms to describe your graph. And you're predicting things like what labels are missing in my graph, where are relationships gonna form in my graph, and what's gonna happen next. Each of these steps builds on the previous one, right? I can't do graph native machine learning without a graph embedding to describe my graph. I can't run a graph algorithm like an embedding without a graph in the first place. And depending on your problem, your project, the data you have, maybe you stop at one of these steps, but each one is valuable. Each one builds on the other one. And if you break it down this way, graph data science becomes a lot less intimidating. And so you've probably seen that slide that Neo uses a lot where we say everything is connected. And I like to take that slide and kind of talk about it in the context of graph data science. And so we said graph data science is using connections to answer questions. So if we have our social network, we have our item graph, we have our knowledge graph, what kinds of questions do we answer? Starting off with step one of queries, right? If I have my social graph, I can say, who has the most connections or who else bought the same item in my transaction graph? These are queries to answer questions. As I build on that with my unsupervised techniques, and I want to answer that same question of who's most important, well, that's who has the highest page rank. Or if I want to say, what's the best choice in my transactional graph? What's the shortest path between these two nodes? I can start to build and get more sophisticated. And when we get to that top step of the steps of graph data science, when we're doing that graph native machine learning, in our social graph, maybe it's predicting labels. It's saying, who has the label of influencer? Or in our knowledge graph, maybe it's link prediction, predicting what will happen next. I'm going to predict a missing link, the relationship that will form in the future. And so each one of these, you can see, answers a question in a different way, going from I know exactly what to look for, and I can express that, to I don't know what to look for, but I want to understand what's going to happen next. And one thing that I think is super important when we talk about graph data science is making sure that we don't over-index on a specific use case, right? Graph data science applies wherever you have connections in your data. Some of you all were in the previous talk where we were talking about COVID, right? And that's a biomedical graph. See a lot of graphs there, but we also talk about fraud detection a lot where you have that transactional graph. Maybe you have your recommendation graph where you have people buying items. Maybe you have your supply chain with manufacturers and warehouses and items. all of these are connected data sets, and all of these can help you with graph data science. So graph data science isn't a fraud solution. It's not a supply chain solution. It's just a way of thinking about your data and a way of using the connections in your data to answer questions. So that was the basics. Probably a lot of you all already knew that, but if you didn't, we caught up. So the next thing I want to talk about is Neo4j graph data science. We say those words a lot, but sometimes it can be confusing. Like, what are we talking about? What do we offer? What is this product and how does it help me? And so you've probably seen some version of this slide used before where we talk about the graph platform and that approach to answering your questions, to dealing with data that starts from data sources, bringing that data into our database, running graph algorithms on it. We offer drivers, we offer visualization frameworks, we offer integrations. But when we talk about graph data science, we kind of zoom in on 3 products, right? We have our Neo4j database, which is storing your connected data in a connected shape. On top of that, we have the graph data science library, which lets you run those graph algorithms, those ML pipelines at scale. And then with that, we also have Neo4j Bloom, where you can visualize, explore, and understand your data. And if we think back to that Venn diagram in the beginning where we had queries, machine learning, visualization, these products map to that. So we offer the full portfolio of what you need to answer questions with your data. And when we talk about, what does Neo4j GDS actually do? We really have 3 pieces. We have the graph catalog that underlies everything. This is how we take that underlying transactional graph, reshape it, load it into memory in the optimized format. And on top of that, we use graph algorithms to answer those unsupervised questions, and machine learning pipelines that use that format. They use graph algorithms as features to start answering supervised questions. And now I'm going to spend a little bit more time on each of these. And honestly, we could talk for days. A lot of this deck is just pointers to other talks where if you're like, wow, this is super cool, you can follow up there. So the first thing I want to talk about is the graph catalog, because I feel like it doesn't get enough love. When people talk about GDS, they're like, oh wow, there are so many algorithms. But you never think about how come I can run these algorithms? What makes them work? The graph catalog is kind of our secret sauce. So in Neo4j, in your database, you have stored that data in a transactional store. It's persistent, it's ACID compliant. But now you want to do a data science project. You probably have a specific data set that you want to extract from that knowledge graph. Maybe the data model or the representation of that data is slightly different than what you've got in your whole database. Maybe you want to transform things. The graph catalog lets you do that. So it provides you with a single API to create a graph projection. If you're coming kind of from the relational database world, think of it like a materialized view. It's basically you're saying, this is my underlying graph. This is the piece I want to use for my data science project, and this is the shape that I want it in. And when we do that transformation, you can have multiple projected graphs at the same time. They're updatable. When you do that graph projection, you can reshape your data. You can change your labels. You can combine things. You can transform your underlying data in the right shape to answer the question you want. And this is all about exploration, right? So maybe I have my supply chain graph and I've got a really nice temporal framework, and I say, I want to look at the social network of the people who work at those factories. Well, wait a second. When I create my projection, maybe I can connect people to each other based on the factories they work in and have a transformation of my underlying data. And if that turns out to answer a question for me, maybe it feeds back to my database. Or maybe I say, oh, that wasn't interesting, and I try something different. What this lets you do is you create these in-memory projections. You can update them with the results of your algorithms with our mutate mode. The graph catalog is how you manage all of those. If you saw during the demo today where I was checking graph.list, graph.drop, it's how you interact with those. And a new feature, just to highlight here, is you now have the ability to back up and restore those projections. Or you can export them to databases like I did in order to run Bloom this morning. So this is a really cool, full-featured way of interacting with your data in the right shape for data science. And if you want to learn more about this, Martin from the engineering team will be presenting on scaling into billions of nodes tomorrow morning And this is really a deep dive into how does all of this work? So I recommend that talk. Sorry, Martin. Next piece, graph algorithms. This is where people get excited, right? Graph algorithms are really easy to understand. This is actually doing the question answering. So there's basically 6 categories. There's pathfinding and search, which is often when people think about network science, if you're like, name a graph algorithm, odds are they're either going to come up with shortest path or PageRank. Shortest path is the pathfinding and search. If you work in supply chain, if you work in retail, you probably use these. On this slide, the ones in blue are just brand new ones in the last 2 releases. So those are new. Delta stepping is a parallelized shortest path. We also have centrality algorithms. Those are, I have all this data, what's important? Different algorithms basically use different metrics to calculate importance. This is where PageRank sits. So I said if you ask someone, what's a graph algorithm? Odds are shortest path or PageRank. PageRank was Google's secret to how you figured out what was important on the internet. These algorithms help you answer questions like, who's most important? Where should I target resources? Where do I have a high-risk node in my graph? Next up, we have community detection algorithms. What these are is, if any of you have done k-means clustering before on your tabular data, just unsupervised ways of grouping your data. Community detection lets you group data based on relationships or properties. This helps you find, maybe if you're working in the fraud space and you want to find fraud rings. Community detection finds you, hey, these people interact with each other pretty frequently. That's a little suspicious. Or maybe in the retail sector, you want to look at who's buying what items together and why. And you can find those co-purchasing communities. And these answer really useful questions when it comes to things like segmentation. We have heuristic link prediction algorithms, which are different than the link prediction we'll talk about later. This is rule-based. So basically, I have 2 nodes. Should there be a relationship between them based on how many neighbors they have in common, or they're in the same community? And these are often a quick way of kind of figuring out things like triadic closure. We have the similarity algorithms, which often people get very excited about because they make a lot of sense. They're easy to understand. I want to understand which nodes in my graph are similar to each other based on the topology of my graph. In our latest release, we've added the ability to filter based on source and target nodes, which makes your ability to do similarity much more fine-grained. And last but not least, and kind of my favorite category, we have our graph embeddings. And these are basically the one algorithm to rule them all. The graph embedding learns a representation of your graph based on the structure of your data set, and you tune it to answer the question that you're trying to answer. So all a graph embedding is if you think of your graph as that 5 billion by 5 billion adjacency matrix, a graph embedding is just a low-dimensional numerical representation of each node in your graph that encodes all of the information that's in that highly complex graph into just a couple numbers. And you can see where that's really the linchpin between graph algorithms, where I want to use unsupervised techniques to learn how to represent my graph, and supervised machine learning, where you're doing feature engineering and then making predictions about your graph. Which is our next section, machine learning pipelines. And this is probably the newest piece of the library. We introduced this about a year ago. Machine learning pipelines help you do that in-graph supervised machine learning. We offer 3 different types of pipelines. Node classification, which is basically figuring out the missing labels for your graph. So fraud, I have people, they're transferring money to each other. Some people are labeled as fraudsters. Who's missing that label? Or maybe you have a retail graph and you have people buying services and you want to predict who's going to churn. Churned customer is a label you can predict. We have link prediction, which is predicting those missing relationships in your graph or relationships that'll form in the future. And brand new, we've introduced node property regression. So this is if node classification can fill in a missing label, node regression can fill in a missing property based on the topology of your graph. The way we do this is with pipelines. And so the tricky thing with graph-native machine learning is graphs are complicated. You can't just dump your graph into a table, randomly split it, and hope for the best. Or you can, and it might seem like it's great, and then you're going to deploy it, and then you're going to be really sad because it will be terrible. And so it's hard. And so we try to make it easy. So our pipelines basically let you define all the steps you need. So what am I trying to do? I want to predict node labels. What is the data that I want to use? What are the features I want to put into this? How do I want to rebalance my data? How do I want to evaluate my model? You define all of that, and then we execute the pipeline for you in the correct sequence of steps. We do the data splitting and rebalancing. We do the feature engineering on the correct subgraph so you don't get data leakage. We do model evaluation and selection for you. So you say what kind of model techniques you want, what parameters you want to explore, and we return the best performing model based on the criteria that you specify. And in our 2.1 release, which is GA on Thursday, we introduced the ability to do automated hyperparameter tuning. So what that means is you can say, these are the parameter spaces I want to consider. Neo4j, go find me the best performing model and let me know when you're done. And it's basically, an automated ML solution to build those ML models to predict your graph structure. And then once you have that model, our secret thing is we're a database. We're really good at storing stuff. So you train that model, we store it in the database for you. We have a model catalog to manage the models you've trained. If you like the model you've trained, it's persistable, it's publishable. So let's say I train a model, I train 10 different models and 9 of them are embarrassing and I want to throw them out, but one of them is good. I can persist it, I can publish it so the rest of my team can use it, and then I can apply that model to new incoming data in my data set or unlabeled data. So it really makes it possible to deploy graph-based machine learning to your production database, which is pretty cool and something that we're really excited we've been building. Cool, so that was a rundown of how we think about the library, the parts of it, how it works. Next question, how do I deploy this and where? And so the first thing is, there's a couple different architectures you can use depending on what you need to do. So I think when I started at Neo4j, I probably spent my first 6 months on the job saying, please stop trying to run GDS on your cluster. Because they're not friends, they're built for different types of workloads. Your cluster is fault tolerant, it's ACID compliant. GDS uses a lot of money, or a lot of memory, also computing money. But GDS uses a lot of memory and the algorithms are slower, right? Let's say you want to train GraphSage on your large graph. Well, that's going to take a while. You don't want that tying up your cluster. So kind of our default deployment model is a single instance, a large single instance dedicated for data science that you're running that graph data science library on top of. But a lot of people need more flexible deployment options. So a few releases ago, we introduced the ability to add read replicas to your GDS instance. So I have my primary compute instance running GDS with all my data. Then I can add read replicas that keep that same data in sync for read scaling if I need to run queries. Or maybe I want to have a Bloom server that's not fighting for resources with my primary node. Or maybe I want to have disaster recovery where if my data science team happens to kill the database, I've got another copy. But then the newest architecture that we've introduced with our 2.0 release is actually hybrid deployment. So now what you can have, and probably a lot of you in this room do have causal clusters that you're running with Neo4j, and you're like, but I want to do graph data science. And maybe you didn't listen to me and you were like, I installed GDS on my leader and it was a bad experience. But now we provide you with a recommended experience. You can attach a GDS node to your cluster and we manage the write back for you. So you execute your GDS algorithm calls against that GDS node. We handle write back to the cluster. You can kind of tune things for better performance, but that GDS node gets the updated data from your cluster, from your transactional application. And we're not fighting with your cluster, fighting with those transactional reads and writes for resources. So you have your fresh data in the same place as you have your analytic workloads, which is pretty powerful when you start talking about productionizing your workloads. Okay, cool. So you choose your architecture. You can deploy where you want, right? We have self-managed GDS, where you can get the binary, you can deploy it on your cloud of choice, you can deploy it on-prem, you can choose the architecture you need. We have Docker images A lot of people who want to use GDS transiently or just kind of experimenting, use Docker. It's a great way of getting a pre-configured environment. And we also have introduced Aura DS. Some of you have probably attended the workshop yesterday about using Aura DS. This is basically our managed service. We handle the infrastructure, so you focus on data science. I am trained as a data scientist. I am a terrible DBA. You probably don't want me trying to keep your cluster up. Neo4j handles that for data science teams. So you focus on getting value, we focus on behind the scenes stuff. And if you're interested in that one, we're gonna have a whole session on it tomorrow, so I'm not gonna steal too much of Luke's thunder. Or I will. It's all about making it easy. We offer sizing guidance, we offer scale on demand, metrics, migration and cloning. So all you really have to do is say, these are the algorithms I want, and this is how big my data set is. Tell me what I need, right? It's super simple. Data scientists don't have to figure this out for themselves. We also monitor the health of your instances. You can look at CPU usage, you can look at storage, heap, out of memory. We handle all of the monitoring, so you focus on what you need to do. Now, if you want to learn more, there's a session this afternoon where we're going to spend 40 minutes learning all about Aura DS, capabilities. Everyone should go to that. And I'm getting eyes from that. So next question, ecosystem. Probably a lot of you came from Zach's talk, where he talked in depth, did a demo of how do you use GDS with everything else you use. So one thing that's kind of unique about data scientists and data science is we don't exist in isolation, right? Often, I'm a data scientist. I get my data from a data lake. I have some downstream application I have to feed my results into. Ecosystem becomes much more important. So we have lots of different supported connectors. We have the Spark connector. We have the new data warehouse connector, which Zach talked about earlier. We have our Kafka connector for streaming data. We have our BI connector if you use Tableau downstream. And we have lots of drivers for your language of choice. And we've also introduced our Python wrapper. And so if you didn't join Zach earlier, data warehouse connector is, I think, available now. Documentation coming soon. It's basically, we're using our Spark connector infrastructure to let you execute Spark jobs to move data from common data warehouses into Neo4j for analysis. And so it's all about letting you use Neo4j as part of your tech stack. We talked about this morning in the demo. Another integration we're super excited about is Apache Arrow. This is new in GDS 2.1. If you saw the demo this morning and it kind of seemed like sorcery and you were like, what are they talking about? Why is it so fast? Why do they keep saying the word arrow? Arrow is basically a way of formatting your data that lets you move it really quickly. It's an in-memory representation. We use a flight server to move data from source to target. GDS 2.1 lets you use Apache Arrow for graph projection, which is what I was demoing. Database creation, where the graph projection creates that in-memory view of your data. If you're using GDS transiently, that's all you need. You can also use it to create a new Neo4j database. We also use it to let you export your algorithm results really, really fast. So some of you, if you've used GDS before, you may have run into, cool, I made my embeddings, I want to use them outside of Neo4j. And then you tried to use our Python driver and you were like, I can't get them out. I hate this. And so that's kind of where Apache Arrow integration was born. And again, I said I have a lot of pointers, a lot of advertisements for other talks. If you like this one, we have a whole session about Apache Arrow, how it works, how we use it, and how you can use it for really fast ingest. So next thing I want to talk about is our Python client. This was another thing we kind of glossed over in the demo. If you code in Python, you might have been like, wow, her code looks kind of different than what I'm used to. With GDS 2.0, we introduced our native Python client. So you just import graph data science, and you can use GDS just like you would any other Python library. You don't have to sort out Cypher. You don't have to understand transaction functions. You can treat your graphs and your models as objects, and makes it much simpler to integrate GDS into your notebooks. So if I want to run an algorithm, it's just gds.fastRP. If I want to interact with a graph object, I just have that defined in Python. And so it makes kind of the barrier to entry much lower and the experience much smoother. And again, another pointer to another talk. We have a lightning talk today about using graph machine learning pipelines with GDS 2.0 and Python. So I recommend that one. And finally, the bottom line here is that GDS is part of your tech stack. We aren't asking you to throw everything else out. We're asking you that if you've got graphy data, if you've got connections, we're the place to analyze that, and we fit in seamlessly with everything else. Cool, so we've covered a lot of ground. I want to kind of end on what else is new? If that wasn't enough, we've said a lot of other new things, but I kind of want to end on some other highlights that maybe don't get as much prime time because they're not as demoable as, wow, this was fast. So we have a new release, 2.1, coming out on Thursday, and we've got 2 new algorithms in that release. The Leiden algorithm, which I bet some folks in this room have requested. There was a great paper a couple years ago, basically saying, hey, Louvain is a great algorithm, kind of creates disconnected communities sometimes, which isn't great. Let's change that algorithm. It's a hierarchical modularity-based algorithm for community detection. We've added it into the alpha namespace in 2.1. We also have finally added k-means clustering. This was another frequent user request. I created my embedding and I want to stay in the unsupervised world. I don't want to train a pipeline. I just want to see how many clusters I have. Or I have some properties and I want to cluster my graph based on that. K-means clustering, you get to say, I want this many clusters. We assign those labels. Another advertisement. There's a whole talk tomorrow on interpreting the results of community detection algorithms using these included. So I told you this was an advertisement session, getting your full value. Next thing I want to talk about that isn't always front and center is transparency and logging. So one of the things that we've really invested in is making GDS usable. So we have some algorithms that take more than a millisecond to run. And your initial experience might have been, I hit enter, and now what? And you might have filed an issue, and I said, go look at our debug log. And you said, what's that, and how do I get access? So recently, we've added progress logging. So you can call a function list progress, and you can see everything running, the percentage done, when you started it, its current status. Most recently, in our Python client, we added this little progress bar. And this is just a little widget, but in real time, it updates as your algorithm executes. So you can see, how long has this been running? Can I go get a cup of coffee? Should I come back tomorrow, next week? Useful stuff. We've also added system monitoring, and you can think of this as a level up. So I have a team of data scientists, and my instance is not responding. What's going on? System monitoring lets your admins get that global view of who's running what resources are available, how much memory do I have left? Oh no, Alicia has decided to run GraphSage on all the cores, and that's why this isn't responding anymore. And so it helps you manage multiple users and understand how they're using it. And finally, in our last release, we also added hints and warnings. So if you're running GDS and you're like, it finished, it executed, but was that right? And we don't know if you were right. Did you intend to do that? It seems okay. We can print warnings to the user log. So in this example, I ran weakly connected components. I gave it a relationship weight, but I didn't set threshold. Was that what I intended? Like, did I want it to ignore that? Or did I make a mistake? Instead of just failing the algorithm and saying, I don't know, you can't run this, now we say, hey, in the user log, when I ran WCC, here's a hint. And it's up to you to figure out if you want to fix it or not. And then I already kind of touched on this, but when we talk about GraphML and what are our capabilities, we added property regression, so kind of finishing that missing piece. So I can predict labels, I can predict relationships, and I can predict numerical properties. And I mentioned auto-tuning, and this is what it looks like. It's just a step in your pipeline where you say, configure auto-tuning, here's what I want to tune, and then we find the best model for you. And then ending with, we are going to use this slide to death. We are very excited about letting folks run algorithms on scene from Bloom. This is a great way to explain what you're doing, experiment and iterate quickly in scene, but also, if you don't know how to use GDS syntax yet, if you just want to see if there's something there, Bloom lets you do that. So we're really excited to be introducing that. And with that, we've had kind of a whirlwind tour of graph data science, what it is, how it works, how you can deploy it, what's new. And I'm happy to stop and take questions.